Okay, we are back for the second class now. Let's see 3 more examples, and let's see 3 more examples, and then we are going to cover the homeworks for the last homework, most probably for this semester. So, okay, here it is, the homework. Then we can start. So I'm sharing the screen. Now let's see another example. So we are finished with this stuff, mutexes and threads. Is there any questions? Is there any question about mutexes and threads and whatever we saw up until now? So you know what the process is, you know what the thread is up until now, and you know what the mutex is. And mutex, by the way, comes from the word mutual exclusion. Okay, meaning that it excludes. So this is mutex. It means that it excludes threads from simultaneously accessing shared resources. Okay. If you don't have any question, then we can see another problem when we use parallelism. So, or pseudo-parallelism, and when we have critical regions. So you want to have pseudo-parallelism to speed up things, to execute at the same time in pseudo-parallel manner multiple processes. But as you see, you encounter problems. I showed you 2 problems, the spooler directory, the cout stuff, and we'll see another problem right now. Now let's see how we are going to solve it. So basically, let's go with count 3k example. This is my example. Okay. Let me run system pause over here, write it. Now, I want also this to be interactive. We have a function count. Before that, we have global variables. Counter is equal to 0 and CTR is equal to 0, and maximum is equal to, let's make it 1 million. Not 100,000, 1 million. Now let's not use mutexes for the time being. This is what I'm doing. Let's not use this one also. So basically in my while loop, while counter is smaller than maximum, I just increment counter and CTR plus plus. Now, if we run the count function in an ordinary manner, in a manner that we have been used up until now, what do you think is going to be the output? So maximum is 1 million. So can someone of you tell me what should be the output of counter and CTR plus plus in normal circumstances that we have been used up until now? Okay, please let someone write, or maybe he or she can use the microphone to tell me. In normal circumstances, what should be the output of the variables counter plus plus and CTR? It should be it should be 1 million NS, because if it's 99999, it's still smaller than the maximum. So when it goes, it's going to increment itself by 1 again, and it should be 1 million for both of them. Okay. Thanks for the answer. However, let's run the code and let's see whether it is the case or not. But by the way, before running it, so we have the function count. We declare an array of threads. This is also doable. From 0 up until 6, we assign those threads to run the function count, all of them. Then we join them because we don't want main to finish before them. So main, remember, is also a thread. And in the end, we print the value for CTR and the value of counter, which are, again, I repeat, global variables. So whenever those threads call this function count, they actually access those global variables, counter and CTR, okay? And they kind of try to increment them. Yeah, we expect the last output would be 1 million for both of them, okay? But let's see whether it is the case or not. So let's see the output. I'm dealing now with 6 threads, which all of them try to, in pseudo-parallel manner, to increment the global variables counter and CTR. Now let's see. The output for count is this one, and the output for counter is this one. Wow. Weird. Okay, I have like 10,000 or so less counts in the first one. Let's run it again. And here I was very lucky, very, very lucky with it. And here I have something else. So I get inconsistent outputs most of the time. Usually it's not, we're not that lucky, but okay. So when we run the code, each time we get different outputs. Okay, so this time I have like 100,000 less approximately counts for count than the counter, for CTR than for the counter. Now let's see what is the problem. In order to see that, let's go with maybe this one. So let's see what's happening. Let me write the, so as you know, C++, C, Java, Python, Visual C#, and others, they are high-level languages. Computers don't understand them. What we do, we translate them into low-level languages, which is the assembly, ones and zeros, actually, even not assembly. This is the language that the computer understands. That's why we compiled it. Basically, we translate it to a language that the machine understands. So let's write the code in C++. In that code in C++, let's say we have something like this: counter plus plus. So this is C++ code. And we have the corresponding assembly code. So with the assembly, what do? We have something like this: fetch value. Fetch value means get value. Increment. Put value back. Okay, so what is only counter plus plus or CTR plus plus or whatever? Actually, in assembly code is going to be 3 lines. Okay, this is how it works. This is how approximately it's translated from the computer. Now, why do we need that? We'll see it in a while. It should be not, it should be counter. Okay. So only 1 line of code in C++ is actually a lot of lines in assembly language. Now, let's assume, okay, this is one process, this is another process or thread or whatever. And let's call this maybe thread 1. And this is my thread 2. Okay. And here we have the counter variable. So we have the counter variable over here. And let's say that the value inside the counter variable is initially, let's say, I don't know, 5. Maybe we can put both of the variables here, counter and CTR plus plus, both of them. And let me do the same also here. So CTR plus plus. And remember then both the plus plus stuff is actually done in assembly code like this with those 3 lines. So we have the counter and we have a CTR over here. Let's also assume that the value of CTR is also 5. Now, it's time for thread 1 to start, okay, and run the code. So what it's doing is the following. First, it's executing counter plus plus. When it's executing counter plus plus, actually it's doing the assembly code, not the C++ code, okay, because it's compiled, it's translated into assembly. So I'm fetching the value, which is 5, for counter C++ now first. Incrementing it, it's 6. Put value back, it's again 6. Okay. Now I do the same for CTR. Okay. So I'm finished with counter plus plus. Now I should do the same with CTR plus plus. Basically, I fetch the value, so I'm taking 5. Increment it, so it's 6. Put value back, okay, because those are called registers. They are separate memory, and the core of the processor has some separate memory. Basically, when you increment something, you take it from the memory, put it to the local memory of the core of the processor. It does the incrementation inside, because it has an arithmetical logical unit inside which can do the operations basically. After you do the operations, you put it back to the memory, to the register as it's called. Okay, this is how it works. But just when I want to put the 6 back of the CTR, the compiler says, okay, stop. Now it's time for thread 2 to execute. Okay, and okay, thread 2 then again starts with counter C++. Basically, it fetches the value. Now count the value of counter is 6. I'm taking 6. Increment it. I'm making it 7. Put the value back. Okay. So I put the value back now. It's becoming 7. In similar fashion, I continue with CTR plus plus. Fetch the value. So I'm fetching the value is now 5. Fetch means take, get. Increment it, 5 becomes 6. Put the value back, and I'm putting the value back. I'm putting 6. And then I'm finished. And the operating system says, okay, now it's time for thread 1 to continue. Now when thread 1 continues, it should put the value back at CTR, where it left. But hey, the value that thread 1 has in its core arithmetical logical unit is 6. So when I put back, I'm going to put 6 again. So I'm deleting the 6. And I'm putting the 6 that thread 1 has. Now both of them, thread 1 and thread 2, have executed counter plus plus, CTR plus plus. Okay? Initially, if you remember, the values were 5 for both of them. Okay? So thread 1 incremented it, thread 2 incremented both of them. However, as an output, we see that the counter was incremented twice, as expected, but CTR was incremented only once. Why did it happen? Well, because of race conditions and the critical region being accessed from multiple threads, in this case 2 threads at the same time. This is how you lose one count. Of course, if you repeat it hundreds of thousands of millions of times, you'll see more counts lost. Okay, now we know why do we have this output, unexpected output with counter and CTR plus plus. Okay, why do we lose counts actually? So how we can solve it? Very easy, very easy. Whenever, so where was my code? Whenever I'm trying to access something which is a shared resource, I just lock it, okay? So basically here, I should put lock. And in the end, unlock. So when I lock a resource, no one can enter it without the thread unlocking it, okay? That's why in our piece of code over here, we are just going to lock and unlock. And what's going on is the following. Basically, if, let's say, thread 1 has locked a resource, let's say counter, then thread 2, when the compiler gives its time to thread 2, it tries to lock it also, but since it cannot lock it, because it's already locked from someone else, it's going to wait. Basically, we are wasting time over here. That's why it takes more time to execute those pieces of codes. Maybe, I don't know, depending from the environment and other processes being run, it might take even 1 minute to execute this piece of code. Okay, otherwise it takes maybe a couple of seconds. But it takes more time, that's why let's deduce it to maybe 100,000. And now we shouldn't have the problem of different counts because we lock it. Okay, we have it, but let's do it this way. Okay, so this is what we should get actually. Okay, because we lock the resources. Actually, I have some objections towards this code. Why do I have an objection towards this code? Because we use only one mutex. We use only one mutex, and this is not how it should be done, because we have, as you see here, 3 shared resources. So basically, we should use one mutex for CTR, and maybe we should use another mutex for counter. So basically, I say m2.lock, and again m2.unlock. This is better. But the idea is that it's no need to use m2. Why? Although I don't agree totally with that. Why the idea is that we don't have to use m2? Because when one thread is working with CTR++, it doesn't let the other one come here. And the other one is not working with CTR++. Basically, it's working with counter++. This is the idea, but it's not always the case. Because sometimes one of the threads can be stopped while it's working with counter. That's why sometimes you get, not often, as previously, but sometimes you get an output where counter++, when counter and CTR do not have the same values. Okay. Okay, here we have it. We're a bit lucky, but if you put 2 mutexes, you almost never get the different values for both of them. Okay, so this is how it works. Now, let me give you some rules about mutexes, how to use them and when to use them. First rule, so you should have mutexes as much as you have global resources which are shared. If you have 2 global resources which are shared that we are going to use in your code, you should have 2 mutexes. Okay. So in this case, we have 2 variables, counter and CTR++. So it's smart if you have 2 mutexes. If you're going to use cout, another mutex for cout, which is shared. So you have mutexes only for shared resources. And by resource, I mean queue, variable, objects, whatever. Furthermore, if one thread is not accessing critical region, it should not prevent the others to access it. Okay, so sometimes you might make a mistake. No thread is not accessing, it's not working on the shared resource. It's not accessing the shared resource, but it's preventing others to access it. This shouldn't happen. This is rule number 2. And rule number 3, try to put the locks as closer to the shared resources as possible. Okay, we're actually going to see examples like that, but try to put them as close as possible. And we are going to see those rules with examples. If you don't have any question, then we can proceed with the other two examples. Let's see if there's a question. Okay, so in main, Jamil, instead of just doing, it's not an array, it's only one array. Instead of doing like thread and like thread 1, thread 2, because I want to have 6 threads. So I can have mistakes in my output. I just do it with an array. And it's much more easier to declare an array and then give to those threads array, okay, all of the threads of the array, which is a thread array function to deal with, and then I join them. As simple as that, okay?
Can I ask something?
Yes.
So like, doesn't each index of the array increment the counter and CTR? So won't they be greater than like 100,000 or 1 million, whatever you?
Okay, so if I have something like this, integer, my array 6, and then in the for loop, if I do something like this, okay, I just assign values to my array, okay, my integer. Well, with the same for loop, I just assign task to the thread, which is the function count, and they all run the function count, okay. And since the counter and CTR are global resources, of course, some race conditions are going to have to happen. That's why we do it. Hope that answered your question.
Okay. So in the end, the value that we get is like, is it from one index or is it like the total value? Like, because isn't each index incrementing the counter and CTR? So
yeah, not each index. Each of the threads is trying to increment it. And this is so basically all of the threads combined want to make sure that this counter is smaller than maximum, and all of them increment it. Okay.
Okay. So if we had just one thread, would we not receive the same output?
If we have only one thread, we will not have the problem. Okay. If we have only one thread, it's going to work with what the problem is. If you have multiple threads, then the race conditions appear, those unexpected outputs. And our aim is to simulate these unexpected outputs, because often, as we're going to see in the upcoming examples, often threads share the resources. Okay, maybe this looks stupid, but our aim here is just to show with an easy example to see when threads compete, or when threads share resources and want to do the same job, that some inconsistencies might happen, and let's see how we can solve them. Okay.
Okay, so this was just to show the race conditions.
Yes, just to show the race conditions. This is our purpose here. Maybe the next two examples are more logical. Okay. Yeah, of course. One thread should be enough. Of course, even you don't need a thread for that. You just call the function count. Okay. But it's not always the case. Sometimes multiple functions should be run by multiple threads, and we will see examples of that, especially in the last example. And your homework is related to that, actually. Okay, so let's start with, if you don't have any question, let's continue with another example, which is similar to this one, but a bit more complicated. It's increment-decrement. Okay, so what do we have here? Again, we have global variables, which are a mutex, a global count, a constant integer, which is decrement threads, another constant integer, increment threads, which the number of both of them are 2. Then we have an array, which is called iterations, and it has 2 plus 2, which is 4 elements, and the value of them are 5 for each of the elements of the array. Then for random numbers, which is what you're going to use for your homework, you use this function, not the randint from CS201, because it's not thread safe. This is thread safe. Okay, so you just give a max minimum, a maximum, and you return something which is random between min and max. Okay, now we have functions. One of the two functions actually, increment and decrement. And those functions are going to increment the global count, the global variable called global counts, by random increment or decrement them by random values. Okay, so the function increment, it takes a thread ID as an input, the thread ID that we give, not the compiler. And in iterations, actually iterations here is 5 because we give for each of the threads. So starting from 0 up until 5, and 5 is not included, basically in 5 iterations, the thread is going to sleep for 100 milliseconds, you know the sleep for functions I just told to you. Then what we are going to do is the following. I'll randomly choose a number between 1 and 5 and give it to increment. Then the global count is going to be incremented, this global count over here. It's going to be incremented by it. And I'm going to print that I've actually, that thread with this thread ID that I gave it, incremented the global variable by this much incremented value. Okay. And of course, iteration plus plus, and then I'm finished. In a similar fashion, I have the decrement function. I'm also taking the thread ID as a parameter. Iterations go from 0 up until 5, 5 not inclusive, of course. And just like here, I randomly pick a value between 1 and 5 and increment the global count. Here, I do the opposite. I decrement it. Okay. Then I print it. And finally, I unlock the mutex. You see, I lock the mutex whenever I access shared resources. And the shared resource over here is the global count. And cout, of course. We had the problem with cout previously, which I explained it to you. So that's why we lock the mutex over here. Although I have some objections, I'll come back to the objections of my code. And we'll let you know where are my objections and how we can solve them. Anyway, so this is what the functions are doing, okay? I log them, unlock the shared resources. In this case, we have two shared resources, the global count and cout. Finally, in main, again, now I declare a thread array of increment threads plus decrement threads, which were 2 plus 2, of 4 threads, a thread array of 4 elements of 4 threads. For all of them, starting from 0 up until 4, this is what I do. If I is smaller than increment threads, basically the first 2 threads, to the first 2 threads, what do I do? Well, I assign the increment function to them, and the ID that I give to them is I, okay? And to the second 2 threads, I assign to them the decrement function, and I give, again, I. Okay, so 2 threads, first 2 threads do the incrementation, the second 2 threads do the decrementation. And of course, I join all of them. So main is waiting for them to finish, then main finishes, because you never know with the scheduler, main might finish first. Now let me run the code. Let's see the output. Every time you run the code, of course, you're going to see different outputs. So this is how it goes. In the end, it's -12. If I run it again, I might have something else. It's 0 in the end, etc. Okay, but there is not inconsistency here. Everything works smoothly. Now, I have 2 objections. We have 2 shared resources. One is the global count, one is the cout. However, for both of them, we use only one mutex. Now, what if one thread is working on cout and the other one is working on the global count? Well, the rule says that if one thread is not working in a shared resource, it should allow the others to access it. And in this case, it's not. And here it's not the case, because maybe, I don't know, thread 0 has locked the mutex, f mutex, but it's preventing the, and it's now maybe working on global count, incrementing the global count, but it's preventing others to maybe work on cout, which is not doable. This is my first objection. Second objection, mutexes should be as close to resources as possible. Now, as you see here, this integer incremented is kind of a local variable. And why should I waste time for the others to do this local variable thing inside after I've logged the mutex? The smartest solution would have been like this. Cut this guy and put it over here. Okay? Because it's local now. Why should I lock it for something which is not shared? Okay? Because it's wasting time. Furthermore, iteration plus plus. You see, iteration is also local for this one. Iteration plus plus should also be outside. So this is the first thing that I have objections of. Okay. Now maybe this is better, and it is better, of course, because now the others shouldn't wait for the incrementation to randomly find an increment, any iteration stuff. But furthermore, as I told you, so 1, mutexes should be as close to shared resources as possible. 2, if one thread is not working on a critical region, it shouldn't prevent the others to work on that. Okay, and here it's not the case. That's why I propose to have another mutex, and I'm going to call it maybe global count mutex. Okay, and it's for the global count variable, not for the file or cout variable. So this is what I'm going to do. Dot lock. Okay. Dot unlock. You see, I'm as close as possible I can be. And for the file mutex, or maybe cout if you want, this is what I do. Of course, I don't have it here because it's going to be problematic if I have it there. So this should be the code that I'm looking for. Okay, this is much better and faster. Okay, and of course you can do the same with this guy over here. Just instead of incrementing, you should decrement it. Otherwise, everything is the same. Okay, this is a better code. So for each shared resource, you should have mutex, separated mutex, and when a certain thread is not working in the critical region, it should let the others to work in that critical region. Okay. There's a question. Let's see the question. It's just to simulate latency, okay? Because sometimes to simulate latency, because sometimes when you do simulations, you do, let's say, network simulations or whatever, but you do everything around machines. In order to simulate latency, you just make a thread sleep. Okay, this is it. And maybe to show you how sleep4 works. And sometimes sleep4 has meaningful reasons to use it. Okay, and we show it how it's being used, basically, the syntax of it. Okay. Any question? Of course it would work properly. Okay, we just give you the impression of latency, because maybe when you do stuff, actually, there's some processing going on, and when you log something, it's not just increment decrement. You take it, process it, blah blah blah. Maybe it's a file shared by multiple threads, so you log the file so no other thread comes, and then you count the, I don't know, the characters, vowels, blah blah blah, etc. So it takes time to do that processing, and we simulate that with, you know, sleep 4. Okay, that's why. But of course, we don't want to complicate things more. We just want to show how threads and mutexes work together. Instead of sleeping, maybe we could have done some processing over here, but we don't want to do that. Real processing. So if there's no question, I hope you understood it, then we can continue with the next example. Now, finally, let's see the last example and let's explain the homework. So the last example is actually related to your homework. Let me share the screen then. Okay, so the last example is this one. Producer consumer problem. Okay, so we have here a queue of a header and the corresponding CPP file. And for the queue, I'm not going to go into details because, you know, with the queue you have stuff that you should, the most important thing is that you have the function enqueue and dequeue. So basically we enqueue from the front and dequeue from the rear. And it works in first come, first served order. But we don't do it here with linked lists as we have done it. We use array here, but the idea is the same. Of course, we have the function isFull, which returns true if the queue is full, and isEmpty, which returns true if the queue is empty. And we have the corresponding CPP file of that guy. So what's going on basically is the following. Let me show it to you. So this is my queue. Okay, and in that queue, we have a limited number of elements the queue can have, maybe 10 or so, something like that. Okay, so this is my queue. So the index is 0, 1, 2, 3, 4, 5. And here we have a producer which produces items and consumers which consume items, okay, from the queue. So the job of the producer is to produce an item and put it to the queue. Maybe item 1, item 2, item 3, item 4, etc. Okay, and the consumers, the job of the consumers is to take items that, let's say, consumer 1 item is, you know, they take it from the rear. Okay, the producer produce from front, consumers take it from rear. But the problem is the race conditions might occur when two consumers want to take the same item. Okay, and now which one is going to take which one? Well, that's the problem. Okay, and so we have a shared resource, which is in this case a queue. Okay, the producer is producing items and puts them into the queue, and the consumers take them. Okay, but they should take them in an order because, you know, we don't want to see the inconsistencies like we saw it with the counter or with cout or with the spooling directory. Okay, when someone thinks that a user thinks that he has uploaded his documents to be printed, but actually he has not due to race conditions. So this is our example for now. And the queue has limited elements, of course. And the producer should check whether the queue is full or not, because what might happen is the following. The queue is, especially with the consumers, this might happen with the consumers. So let's say that we have only one element here. Forget about the others. Let's say this is my item over here. And both of the consumers wants to take it, this item. So how do they do it? They check, this one checks at the same time. We don't have other items. Assume that we don't have those items over here. Only one is left. So what's going on is the following. This consumer checks, is the queue empty? No, it's not. That means I can take an element. There is at least one. Now let's suppose that there is actually one. And just before this guy is trying to dequeue this element, the other consumer, the operating system says it's time for the other consumer to write, to continue executing. So this consumer checks, is the queue empty? No, there is only one element. And then the compiler stops it. And then the first consumer continues, and it's going to dequeue this guy. So he actually is becoming empty. And when this consumer tries to dequeue this guy, okay, actually cannot dequeue it. But before dequeuing, he checked whether it's empty or not. However, due to race conditions, okay, so consumer one is checking, is it empty? No, only one element left. Just before taking that element, it stops. And the other consumer checks, is it empty? No. And it maybe takes the element. Now it's empty. Now it's time for the consumer one to continue. And now consumer one already checked that it's not empty, but unfortunately, due to race conditions, now it is actually empty after the check is done. So consumer is trying to dequeue an empty queue, which is not doable. That's why for this shared resource, we are going to use, again, a lock. Okay. So let's see the example, actually. So we have a producer function. Okay, so we have a queue, integer queue. It has 10 elements. We have 2 mutexes. My mutex is for the queue, and cout is for cout, of course. And maximus is the number of products that we are going to, consumers are going to consume on average each. We have, so 1 producer, 2 consumers. So what the producer is doing is the following. From 0 up until 2 multiplied by maximum, it's 30. Why 30? Why 60? Because we have 1 producer and 2 consumers. So this producer is going to produce 60 elements. 30 for each of the consumers. Now, I'm accessing the queue. When I access it, I'll lock it in order to prevent the race conditions that I just told you about. And I check it. If the queue is not full, then I can put an element to it, and I can unlock it. However, this if condition, so you might say this is a common mistake. You might think that, oh, I locked it and I unlocked it. But what if this if condition is false? Then we should go with else and unlock it again. Okay, so pay attention. Because if you lock something and if you don't unlock a shared resource, the program is going to stuck. It will never finish. This is called a deadlock. Okay, you locked something and no one can unlock it. It's never going to get unlocked. It's a deadlock. Now, I repeat this loop for 60 times. That's why if I don't, because I should enqueue 60 elements. So if I don't enqueue any element over here, I just decrement I by 1. If I enqueue it, so if the stack is not full, I enqueue it, very nice. Then I'm using this cout mutex to print in cout. Basically, we are not going to explain into details how they work. If you want to take the current time and print it, this is how you should do. Those are the 4 lines that you should use. Okay, so I lock and unlock in the beginning. In similar fashion, this is what the consumer is doing. So since we have 1 producer, we don't have any ID for the producer. It's only 1. But since we have 2 consumers in this case, and sometimes you might have more consumers or more producers and more consumers, then for the consumers, I'm going to have an ID. And I have a counter, which is going from 0 to maximum 30 times. So I lock the mutex. Again, if the mutex is not, if my queue is not empty, I want to dequeue it. So here I check if it's full because the producer enqueues, but the consumer dequeues. That's why it checks whether it's empty or not. If it's empty, I cannot dequeue. If it's not empty, if it's empty, I cannot dequeue. If it's not empty, then I'm going to dequeue it. Okay, and I'm going to, okay, increment counter by 1 and unlock it. By the way, since the counter is kind of a local variable, we can just put it outside. No need to put it inside. Okay, because I told you the lock, the mutex, should be as close to the globally shared resources or shared resources as close as possible. Anyway, If this is not correct, in the else part, I should just unlock it. So always when you have if-else clauses and before that you have locked a resource, you should unlock it in both of them, because sometimes the condition is true, sometimes the if condition is false. That's why. And if you don't unlock a resource, the program will never stop. It will get stuck, basically. A deadlock is going to happen. You're going to see this more when you take the operating system course. Now, we do the same stuff. So when a consumer is taking an element from the queue, it takes it and it needs time to consume it. Consume means to process it. So here I print the starting time of consuming a certain element. Okay, and I just explained it previously. Then I sleep for 10 milliseconds. And then I do the same stuff. In here I print the finishing time of consuming or of processing a certain item. This is it. In main, it's very straightforward. We have 3 threads. One is for the producers, 2 are for the consumers. So thread 0 is the producer. He's dealing with the producer function. Thread 1 and 2 are dealing with the consumer, and I give IDs 1 and 2. I join all of them because main should wait for them, and I'm finished. This is it. As simple as that. Now let me run the code. Let's see the output, and this is related very much to your homework. Okay. So this is the output. Every time you run it, you should get different outputs. This is how it works. Okay. So you see, producer has produced item 59, which is the last one. And 1 finished to consume item 54, 2 finished to consume item 55, 56, 57. 1 started to consume 58, 2 started to consume 59. Now you print also the finishing time. Okay. Each time you write it, you run the code, run the program, you'll get different outputs because it depends from the scheduler on which thread is scheduled when. Okay, so let's go to your homework. In your homework, what you're going to do, you're going to simulate a supermarket. In the supermarket, you have customers and you have cashiers, okay? You're going to have 2 cashiers, as you can see it. And the number of customers is random. Actually, it's going to be an input of the program. The issue with the cashier is that, so let's go to my queue. Okay, so what the cashiers are going to do is the following. Maybe I shouldn't tell you, but actually the producers over here are your customers. And here we had 1 producer, but now we are going to have multiple producers. Okay. And consumers are basically going to be your cashiers. Okay. And you have 2 cashiers always. So when a customer comes, so producer, remember in the code that we explained, produces elements and puts them into the queue. So when customers are going to come, they're going to wait in the queue. So customer 1 came, 1 customer came, or item, another one, another one, another one. And the job of the cashiers is to serve them one by one in terms of first come, first served, okay? So basically, cashiers are kind of consumers from the previous example, okay? Furthermore, there's restriction for the second cashier. The first cashier always works. The second cashier is going to work when the queue is becoming long. And what do you mean by long? There is a threshold. This threshold is going to be an input to the program. Let's say if in the queue there are 2 or more than 2 customers waiting, then the second cashier should start working. Otherwise, only 1 cashier should be there. So think about it. So this is the general idea of your homework. And you have the simulation. You should also generate some random stuff, like inter-arrival time of customers. And for random, as I told you, you should include this piece of code. Do not use in from CS204 because it's not thread safe. For generating random numbers between min and max, this is the function that you're going to use. Furthermore, what are the inputs of your code? The first input that you're going to give is the number of customers that your program would have. In this case, is 15, or maybe let's go with the other example. Okay, so you have 15 customers. Then you should give another input. When should the second cashier start working? The second cashier should start working when there are at least 5 or more customers in the queue. Okay. Then when the customers arrive, there is some inter-arrival time between them. Okay. And you should give the minimum and the maximum inter-arrival time between customers. So minimum is 1, maximum is 3 in this case. So those are 2 other inputs. And there's the checkout time for cashiers. So when the cashier starts to process a customer, it needs time to process it. And the processing time is between 1 and 8 milliseconds. This is also going to be something random. And you're going to use the random function that I just explained. And this is a sample run of it. Okay, now you obviously are going to have some shared resources. I advise you for each of the shared resource, those shared resources should be global. For each of them, you should have a mutex. So what is the obvious shared resource that you're going to have? Well, the queue. So you should have one global queue, just as it was the case with the example that we explained. So you should have one global queue and mutex related to it. Then, of course, you're going to print something. So you should have another mutex for cout. Then maybe, it's up to you, maybe you want to keep the number of customers that are waiting in the queue in an integer. So you might say customer count. Okay. And for this one, you might have customer mutex. But whenever a new customer arrives, you are going to increment it and lock it when you increment it. Whenever a cashier is going to serve a customer, you're going to decrement it by 1, and of course lock it because you don't want critical race conditions to happen. Okay, this is a critical region, shared resource, and this is important to know because as I told you, whenever there was a threshold. So if there are 5 or more customers in the queue, then cashier 2 should start working. Otherwise, it's not going to work. Okay, so think how I'm going to do that. The last example that we showed is going to help you a lot with it. Basically, you should just do some changes in your codes with the last example, and this is it. I told you a lot of stuff, and maybe I deserve 50 points from your homework when you're going to do it. And this is all. Although this is something which is, if you're experienced, you can do it in a very fast way. Since this is the first time that you deal with threads and mutexes and critical regions and race conditions, it's maybe a bit, you may need some time to digest it. That's why I try to do it as soon as possible. So if you have any problems, you can use the office hours on Monday, Tuesday, Wednesday to ask the TAs about this stuff and maybe the professor, okay? So you learned a lot today. We learned about threads and mutexes and race conditions. And we saw why we need pseudo-parallelism and parallelism, but when you deal with parallel stuff, you have this problem that we just saw. So you should deal with it properly with mutexes by locking, etc. So this is actual problems that you see in real life if you're going to work in a company. Okay, guys, this is all for this week. Maybe I took your time more than it was needed, but I think it's better to take like 5, 10, 15 minutes more. So I would explain things better and you will have a better understanding of what's going on and why we need this stuff and to do the homework better. So good luck with your Good luck with your exam. Thank you also, Enes. Good luck with your homework, basically. Check your exams, as I told you, and if you have objections, just write them. You have enough of comments of why did you get a certain grade, but if you still have the objections, you have the videos of your exam that you took. And if there is something that you wrote, but it's not uploaded properly to SUCourse, then you can refer to the video and tell the TA that graded your question that, okay, here's the proof that I wrote the answer, but it cannot be shown, it cannot be seen from the system, so please will you check it. Okay, guys, stay home, stay safe, and see you in the next week.